Reality versus relativity. Theories of relativity attempt to explain what seems to happen when an object inside a moving frame of reference emits light. But seeming is not necessarily reality. Nonetheless, Albert Einstein developed both the special and general theory of relativity from these foundations. Later, Hendrik Lorentz created the universal gamma factor for the transformation equations of Einstein's relativity. Time in a stationary frame of reference has the symbol t, and time inside a moving frame is tau. Both frames share the same route from the light event to an observer. Thus, the distance is the speed of light, c, times t for an observer in the stationary frame, and c times tau for the observer in the moving frame. Lorentz excluded events in space or area, and solved only for the x-coordinate. Then he rejected the math rules for solving events on a line, which gives a linear formula for their gamma factor. Lorentz's squaring produces another gamma factor. This was Lorentz's dirty trick to translate a line into right triangle, used by people who put their faith in Einstein over mathematics. This form of the gamma factor is really the application of the original, which gives the equation for time periods pointing to a place inside the moving frame. As an action runs there, it is during the time period. If a place does not change, then the position on the x-coordinate is the same. Thus a position is excluded during a period. So, they came to the gamma factor mentioned above, which specifies how time inside the moving frame is perceived from outside. For instance, how to perceive a period of life in an inertial frame. This gamma factor says how to compare periods in moving to standing frames. For example, when you take a standard for life in a moving frame to be 1.25 lives in standing frame, then the gamma factor is 1.25. Thus, the rate of life is longer there than in the standing frame. Relativity must have the same speed c independently whether a light travels inside or between frames. Since speed is distance traveled for unit of time, then by keeping the same speeds we have the same ratio for lengths and periods in the moving as standing frame. For example, when a standard for length in the moving frame is equal to 1.25 of the standing one, then the gamma is 1.25 also. But from a moving frame view, our standard for 1 meter is equal to 0.8 of his meter, if the reciprocity relation is not applied. Let's demonstrate more situations to show the constant quotient derived by Lorentz does not exist. The theory comes out when both frames merge, and then one starts to move in the plus direction of the x-axis. Our demonstration here has 4 light events under different angles but having the same distance to the observers in the centers, thus events are on a half circle having a radius of 10 meters. A flash of light occurs 10 meters far from the observers. Both observers would notice each light after the period a light takes to travel 10 meters as far as they are still. The gamma now is equal to 1. When speed of the moving frame is 0.2 of c, then our observer notices as a light from the first event travels on the route 12, the second 10, the third 9 and the fourth that Lorentz considered on 8 meters. Although the observer inside the moving frame sees these lengths to be 10 meters, but according to his time tau, Lorentz gives him 9.8 meters. Also 10 meters are for the observer in the standing, but according to his time t. When the frame speed is 0.4 c, the observer in the standing frame sees a light traveling from the moving frame on 14, 11, 7, and Lorentz is on 6 meters. The Lorentz calculator gives 9.2 meters. Still 10 meters are for the standing frame since it is a radius of a circle. When the frame covers a distance 6 meters by the speed 0.6 c, the relativity determines 8 meters for all lights. But we see, the first at 15, the second 12, the third 7, and the Lorentz is at 4 meters of length. Still, the reality inside the moving frame is 10 meters in accordance with that standard unit of length, which is 12.8 of ours. When we use the speed 0.8 c, the readings are 17, 14 and 7 meters for those under different angles of view. The event on the x-coordinate has the distance 2. Yet, the calculated length by Lorentz is 6 meters for all routes. You see, especially from the animation on the bar graphs, that all lights coming from the moving to standing frame have different lengths. None from all interframe routes matches the calculated ones. Now is time to find multipliers, so the gamma factors, by which the routes inside the moving frame are equal to these observed from the standing frame. We get them as ratio of 10 to the observed lengths, yet it is Ct to C tau. If you pick out Lorentz's situation, appeared lengths are in proportion to reciprocal speeds of the frame. Therefore, these quotients do not match a line on the line graph. Infographics shows hyperbolic lines, as it would be visual representations of the inverse function y equals 1x. Since the Lorentz gamma factors are square roots of expression having squared speeds, then the calculated gamma factors have other curving. All registered lengths to the light event 1 are longer than 10. They do not agree with the Lorentz picturing where Lorentz has them inside the circle having radius 10. Lengths longer than 10 put gamma factors under the number 1, what the Lorentz-Einstein equation does not allow. This makes time in the moving frame running quicker than in the standing. Lights traveling from the event to take interframe routes longer than 10, longer than they are calculated by Lorentz's theory. They make quotients for transformation less than 1 also. Thus, none matches the calculated by the theory. Therefore time in the moving frame should be still quicker than in stationary frame but less than for the event 1. This is because the source of light is near to the y-axis but still in the quadrant 2 of the coordinate system. Lights from the source 3 have shorter routes than 10 because they are under the radius of the Lorentz picturing. Shorter routes means shorter amount of time and therefore time there should run slower. The conclusion is, the relativity saying, time runs slower in the moving frame is not true for the position 1 and 2, and the position 3 in so-called Lorentz situation determine slower time but not in accordance with the transformation equations of Einstein's relativity theory. Some teachers of Einstein's relativity use a right triangle to explain that theory because the Lorentz-Einstein equation can be rewritten mathematically into the form that is known as the Pythagorean theorem. However, they need to have a hypotenuse Ct in two-dimensional picturing, and therefore C tau must create the right angle with Vt. Usually believers in relativity show a moving light clock where light travels up and down between two mirrors. There is C tau, the shortest route between both mirrors observed by the observed in the moving frame. When this traveling is observed from outside, routes appear longer. Since they are routes observed from outside, they have length equal to Ct. However, the scene of the moving light clock isn't the scene proposed by Lorentz. His scenes should be such where lights travel as rays travel from lightning into all directions. The Lorentz-Einstein theory has lights traveling from a firm point to both observers. Thus, Lorentz triangle situation should have a line for a moving frame and two others for light rays traveling from a source to both observers. Since the source must not move and the plus direction be kept, the route from the source to the observer in the moving frame is the longest, thus C tau. Then, Lorentz right triangle situation has another labeling. We may turn labeling back when the reciprocity relation for relativity is applied. Thus, the observer in the moving frame supposes he is still and another frame moves. Then, the shortest route is the route from the source to the observer supposing he is still, and so is C tau. A longer route is Ct for another observer first considering to be in the stationary frame. Since we are in the reverse situation, therefore the reverse situation should cause the quotient to be reverse also. Flipping this situation gives the scene for the right triangle theory for the special relativity. A hypotenuse, there is a route for a light going to the observer in the standing frame, and a leg of the right triangle is a route of a light for the observer in the moving frame. Since the reciprocity is applied, then perhaps we may think about another observing from the source to both observers, and it is as rays would travel from eyes to a moving source of light, a lamp. There is c tau, the root when the observer would move with the lamp, so it is the root inside the moving frame where the lamp shines, and ct is the root from outside as it was observed at the light clock early. Let's have a root inside the frame long 10 meters and speed of the moving frame is 0.6 c. Then a hypotenuse to match time inside the moving is 11.7 meters. The quotient between them is 1.17. The calculated gamma factor is 1.25. Thus, neither the right triangle theory fits to the Lorentz-Einstein transformation. Relation between the right triangle quotient and Lorenz's transforming is reverse, so equal to 0.854. Although we use transformation for the right angle situation by taking advantage of the theory for rectangles, still the trigonometry does not allow us to make such a transformation when a shining light is viewed under other angles because there is a rhomboid. Let's have this right triangle theory for our 4 light events. When the speed of the frame is 0.2 c, then lights are coming from distances 8, 10, 11 and 12 meters, although the calculated length by the Lorentz-Einstein math is 10.2. Notice, the position 2 does not show any dilation between the seen and seamed, thus Einstein's theory does not exist there. When the moving frame advanced by the speed 0.4 c, the relativity determines that the observer in the standing frame will see all lights taking the same length equal 11 meters. But they are 6, 10, 13 and 14. When we have the speed 0.6 c, we observe lengths 5, 11, 15 and 16. The calculated is 12.5 meters. At the speed 0.8 c, the lengths are 4, 11, 17 and 18. The theory determines that they should be 16.7 meters long. The right triangle theory has quotients as ratio of the observed lengths to constant lengths equal 10. Therefore they are 1/10 of the measured lengths. You might notice 3 possibilities in the presented right triangle theory for the special relativity. The observer in the standing frame sees all lights taking the distance 10 meters according to his standard of measuring length. He calculates them by using the speed c and time t measured by his atomic clock having periods equal to 32.6 millimeters for light. Thus all lights travel during 306 ticks. Yet his clock, so is ours, runs in accordance with the first postulate for the relativity. The observer in another frame, which we classified to be moving although he says we move, has all lengths equal 10 meters according to his standard of measuring length. His atomic clock ticked 306 times, thus lights traveled there 32.6 millimeters for a tick. Yet, the base criterion, the first postulate, must be kept to have the theory of relativity legal. And this postulate says that his atomic clock operates by the same physics as ours. Then, there are speculative time and length in other frames due to their motion. For example, whether should one-dimensional or two-dimensional movement at the light clock be taken to know time and length. Our both observers thought about each other time and length due to lengths of lights incoming to them from outside. Hence, when the one thinks that time runs slower and length is shorter on that moving side, the same says that observer about our frame we suppose is still. This vice versa saying must come from other frames in order to stay in the relativity. However, nobody measures these proclamations about other time and length. If he would do, he violates the first postulate and the principle of reciprocity proposed by Einstein at first. Anyway, the theory of relativity is wrong in relation to the gamma factor for the transformation equation of Einstein's relativity. Yet, the relativity is not any physically reality for light transiting from one moving frame to another, since light changes its wavelength and frequency and so keeps the same speed c. If light enters a frame moving away from a light source, then this frame prolongs its wavelength. If it enters a frame moving toward the light, the frame shortens its wavelength. Since we may use instead frequency, the time period for a wave of light, Then we come to the final conclusion: time dilation is change of time periods for a wave of light, and length contraction is change of wavelengths at light occurring at crossings or inertial frames.